As with everything that involves EEG and MEG data, especially in source space, we have to ask ourselves whether we've got the spatial resolution to draw the conclusions that we want to conclude, well, simply to do what we want to do. So this section focuses in particular on the consequences of leakage for the interpretation of functional connectivity metrics. As I said in a previous presentation, there are lots of different functional connectivity metrics, and they all have their different pros and cons. So it's difficult to really come to very general conclusions there. But I think I'd cover the basics that apply to functional connectivity, or actually connectivity, and also with EEG and MEG in general. So let's maybe just start with something that's hopefully quite obvious. So connectivity in sensor space is hard, if not impossible, to interpret due to volume conduction. In this case, I even put connectivity in hyphens here, because I'm not quite sure if one can really talk about connectivity here. So you can, of course, compute phase locking values, coherence, whatever you want for pairs of sensors here in sensor space. And then for a visually evoked response, you might get, not surprisingly, a lot of connectivity between sensors in the back. But you can't really interpret that as connectivity between brain regions. So it doesn't really reflect true connectivity in the brain. So as we've seen before in previous presentations, if you look at the signal in sensor space, there might be a dipole. This is the response to a tone that was presented to the right ear. So you have this left lateralized response here, EEG, here in magnetometers, and you can see that you have these dipolar patterns. And in this case, for one subject, almost looks like a visually evoked response here. Dipole is somewhere here in auditory cortex and just produces the positivity here, negativity there. MEG looks a bit different, but still you have these extreme values here, actually at quite some distance from the true source location. So if you then compute functional connectivity for something like that among sensors, all you can say is that something changes depending on your stimulus or task or whatever you're interested in, but you can't really interpret that as brain connectivity. In source space is a little bit different. So here I would say connectivity without hyphens, can be interpreted, but the interpretation is limited by leakage. So we've seen something like this before. So you can compute for a parcellation of the cortical surface. You can compute these functional connectivity metrics for every pair of regions in your parcellation. So the details here are not really that important. This was just copied and pasted from an Emily Python tutorial or example. Easy to compute. This is based on some cortical parcellation. So you just somehow extract signals for all of these regions, and then you can compute something like an all-to-all connectivity matrix here. But of course, we have to ask ourselves how independent are the estimates for these different regions? I mean, we know that spatial resolution is limited with EEG and MEG, non-unique inverse problem, and all the rest of it. That means we get blurred versions of our true brain activity. And maybe also for some regions that are deep in the brain, it's not really possible to get an independent estimate. Maybe we get a lot of leakage from areas that are just above, here closer to the sensors. Maybe for other regions that are quite big, we could actually have split it in half, and maybe we could actually get more information out of our parcellation. And this is what we could potentially look at using our crosstalk and point spread functions, which we talked about when we talked about spatial resolution. Of course, all of this applies here. So you can actually look at how good your spatial resolution is in your own data. So this is really just a reminder that these exist. We will also come back to this at the end of this presentation, but there are other things that one can do with functional connectivity metrics as well. It's important to realize that this leakage or blurring acts at zero lag. That means it's instantaneous. If you have a dipolar source in the brain, then it produces these dipolar distributions at the surface with zero lag instantaneously. Similarly, the leakage, the blurring in source space happens instantaneously, so there is no time lag between the activation of a source and how it spreads to other areas of the brain. So if we ignore everything that has zero lag, so everything that happens instantaneously, or all the interactions between brain regions that are instantaneous, then we are avoiding this kind of incorrect interpretation of zero lag connectivity. I mean, at the same time, if there is true zero lag connectivity, we will ignore that as well. So we are simply removing some information from our data, but that is something we would have to decide, of course, in advance. So if we are interested in potential zero lag connectivity or not. But the effect of the zero lag connectivity, just to illustrate that again, I think it's been quite clear maybe from what I said before. So if you have one particular source here in the anterior temporal lobe, for example, there's this little green bit here that indicates sort of a little piece of cortex that's active, then you have this spread, point spread around this region, mostly in the anterior temporal lobe, at least somewhat in the area where the signal actually originated, but it can also spread to another lobe here, the inferior frontal lobe. So if you now compute functional connectivity between this region here, let's say just one vertex here and one vertex here, you might get a huge, huge coherence or phase locking values. But this is possibly just due to the fact that both of these signals reflect actually a consequence of the same source here in anterior temporal lobe. So there is no brain connectivity. It's an artifact of our method and this and the leakage here. Similarly, even if we define regions that have nothing to do with with areas where the true activity is, even outside the anterior temporal lobe, you might still see some potential, some functional connectivity here, coherence or phase locking, because this region also leaks into a posterior temporal region and a region here, well, inferior parietal lobe, wherever this might be. So that's also why I would suggest, I mean, even if you run a functional connectivity analysis with regions of interest, always to also check if you can some whole brain distributions, maybe for seed-based analyses, to check whether your regions of interest are actually placed in regions that make sense, that reflect some peak in the overall distribution, for example. Because unfortunately with EEG and MEG, you can have some serious mislocalization like that, and this could potentially produce spurious connectivity results. One way now to deal with this, as I mentioned before, is to simply remove zero lag connectivity, so remove everything, all the relationships between regions that are instantaneous. And without going into too much detail, there are these methods based on orthogonalisation of time courses, some sort of, if you like, a partial regression that makes sure that all the time courses between for pairs of regions here are orthogonal. Again, the details here are not that important, so I refer the interested reader, maybe also interesting reader, to the corresponding papers. And this also exists for the multivariate case. So if you have more than two regions, if you're not just looking at bivariate connectivity, so you can get orthogonalized time courses for a set of brain regions, and then you just have to be careful that you are not using more regions than you have sensors. That means degrees of freedom in your data. And usually these degrees of freedom are also much smaller than the number of sensors because they're intercorrelated and you have noise. So this may work with some of the parcellations that are available, but again, there is a limit. Also, it depends on how many sensors you have in your analyses. So that's something to look into when you're using these methods. I had this slide already in previous presentations just to illustrate, the kind of functional connectivity that's usually applied in resting state analyses, where you use the envelope for bandpass filtered data, and then you look at correlations between these envelopes, between pairs of brain regions, potentially also among a larger set of brain regions. And the idea here then usually is that you have a seed region, and you compute these correlations for vertices across the whole brain, always with the seed region. If you do that without orthogonalizing, you might see something like that. So very high functional connectivity, or in this case, amplitude envelope correlations around the seed region. And that is an effect of leakage, because this activity from the seed, assuming that there is actually some activity around that seed, will mostly leak into areas around it, so within its vicinity. And then you have basically a very high zero lag connectivity with the seed region, which is simply spurious due to this point spread. And any other potentially significant functional connectivity might not even show up because you have this huge peak in your distribution, and smaller peaks might simply not be visible. If you then orthogonalize these signals, so you remove this kind of these zero lag relationships between pairs of regions, including the seed region, you suddenly lose this big peak here. So here the scale all of a sudden of these effects is much smaller. So you even have to rescale your distribution. So that's what they've done here. And then you suddenly see that there is some connectivity between the seed region and even the contralateral hemisphere. And this is something that is something you can interpret as true connectivity, or at least it's more likely to reflect true connectivity than what you see here, which is mostly due to leakage. So I hope that made some sense. And you would see something similar if you use the multivariate version of that. And this is done, I think, this is the standard resting state connectivity. Again, I had this slide in previous presentations. It's just the seminal study that introduced this approach to the literature, and it showed that you can actually get nice correspondence between some fMRI networks, some of the MEG networks, and alpha and beta frequency ranges. So this is quite a standard useful approach. But there's another possibility to deal with zero lag connectivity, and that is to ignore it. And I couldn't really find very nice visualizations that show what these approaches are doing, but I don't think that's necessary for this presentation. So long story short, you use some of the methods that we talked about in the earlier presentation on functional connectivity, phase locking value, or coherence. And there are ways to simply compute them in a way that they ignore any zero lag contributions to your signals. So we talked about the polar representation of periodic signals before, where you have a real axis and an imaginary axis. The real axis reflects zero lag relationships. The imaginary axis reflects everything that has a phase difference between signals. So if you focus your analyses and the connectivity metrics on the parts of the signal that are reflected in the imaginary axis, then you've basically ignored the zero lag part, which may be due to leakage. And there are, for some functional connectivity metrics, there are versions that do that. And that is, for example, the imaginary part of coherency. It's basically coherence without zero lag parts in it. There is a corresponding phase locking value for that. There's also something called the phase locking index, which is a little bit different. It computes functional connectivity not based on the phase locking value across trials, but it takes the sign of the phase locking value and checks whether that's consistent across trials. And as I said several times now, leakage is reflected at zero lag. That means it has a phase of zero. So that does not contribute to this to the sign across trials. So therefore, this measure is also ignoring zero lag connectivity. So there are ways of dealing with that, also described in this tutorial by Bastos and Schaffelin. So if you use those, then you are ignoring zero lag connectivity. And it has been shown that that actually does have quite a significant effect on your metrics. So just very briefly, in this study, the authors looked at measures like group level repeatability and consistency and within and across subjects for different functional connectivity metrics here. And then they classified them into leakage prone and non-leakage prone. That means zero lag and non-zero lag measures. And they found that those that actually were sensitive to zero lag connectivity had much larger values here for repeatability and consistency, which sounds like it's a good thing, but it's not really, because they concluded that this is mostly because they reflect leakage effects, so spurious connectivity. And that is more consistent and more repeatable across participants, but it's not what you want. So the interesting part of our connectivity metrics, the bits that are not due to zero lag, are basically due to leakage, that are the parts that are not artifactual. They are the interesting bits, and they are more variable and less consistent across subjects. So that sounds like we've solved the problem, but I think we should still remind ourselves that the inverse problem still exists. So you can remove or ignore zero lag effects, but that does not remove leakage altogether. So there's still this non-uniqueness in our inverse problem. So just to highlight that, imagine in this kind of in the simulation here, so we simulate true connectivity between these two regions here, and this true connectivity is non-zero lag, so there's some phase difference between the signals here. If we look at this with our standard measures, coherence, phase locking value, that are sensitive to zero lag connectivity, we get something like that. So we see that there's connectivity around, let's say, a seed region here, if we use that as a seed region, and also around the other region. So there is some, it does pick up true connectivity, but it also clearly shows this effect that we saw in an earlier slide. So this is probably, this blob here is due to the leakage of the seed region to its neighboring areas. So you can now look at non-zero lag measures, which means the zero lag effects are gone. However, you still have a blob here, because everything that has non-zero lag connectivity between the true vertices here that we use in our simulations will also have non-zero lag connectivity between anything these regions leak into. So there's also non-zero lag connectivity between this area, which actually which got leakage from the seed, and any other area here that gets leakage from the other vertex here that we use in our simulations. So that means there is still a problem with spatial resolution, but at least we have removed some of the obvious, the most obvious and the most dangerous leakage effects in our analysis. If we want to describe the spatial resolution, then we've talked about this before, we can do that. We can look at crosstalk and point spread functions, but of course you may also want to keep zero lag connectivity in your analysis. So, for example, you might be interested in zero lag connectivity between left and right hemisphere. So I think it's quite likely that they operate at similar time scales, or that they are synchronized in some way at zero lag. So if you want to do that, then you just have to make sure that you look at connectivity between regions that do not show any, that are not affected by leakage, or at the very least, you want to make sure you know which areas are potentially affected by leakage and which ones are not. So this is something you can do with crosstalk and point spread functions. So we've talked about that. I think this is a good point to also remind ourselves, now that we know a little bit about functional connectivity, how these point spread and crosstalk functions look like for certain areas of the brain. So we had looked at an example of the anterior temporal lobe. The green spot here was the simulated source. It mostly leaks into anterior temporal lobe, possibly in the other lobe. So in this case, I would say leakage it's there. So across, even outside the anterior temporal lobe, but it's small. And here there are some other areas which I would consider as actually good spatial resolution. I mean, looking at it from an MEG perspective, where leakage is mostly confined to areas around the true source. And also, just to illustrate, what the reason for this might be. I mean, I'm also showing the magnetometer patterns here, and the ones where you have good spatial resolution are usually the ones where coverage of the source is quite good. So I really get a good idea of the topography here. But it also illustrates that if you would do something like functional connectivity in sensor space, you might not get very far. So what does it mean that you get functional connectivity between pairs of sensors here? I mean, this will not necessarily tell you anything about what's actually really happening in the brain here, in this particular brain region. And then there are some regions that are not so good. So if you go deeper into the brain, and in this case, I just used the minimum norm estimator. Different methods, of course, produce slightly different, or not slightly, I mean, potentially significantly different distributions, but we've talked about that. Then you have to be aware that you might get systematic mislocalization, in this case, towards the sensors here. Also, if you go into depth here, Sylvian Fisher, so the source was somewhere down there. Well, actually, no, sorry, this was an orbitofrontal source, which you can't really see here very well. You get quite a distributed estimate here, including the anterior temporal lobe, depth of the Sylvian Fisher. You don't really see anything down there. most of the activity is spread around more superficial brain regions. So if you do connectivity analysis between or among regions like that, then you just have to be aware that whatever you get from a region here will be completely overshadowed by activity that is closer to the sensors. So you really have to ask yourselves whether the regions of interest you define really make sense and really capture the activity that you are interested in, or whether they might actually capture activity from other areas that are just leaking into the area of interest. So unfortunately, the definition of regions of interest with EEG and MEG is not as straightforward as for fMRI, for example. So if you are using your regions of interest based on previous fMRI studies or lesion studies or just a priori assumptions, you just have to be aware that there are these systematic mislocalizations, and also that there are biases in crosstalk. I can only highlight again, in this case, it's actually the crosstalk functions that are the most important ones. So for the connectivity analysis, it's important to know how is the signal in the area of interest affected by signals from area that are not of interest. So you should look at the crosstalk functions to make sure you know where most of the signals are likely to come from that contribute to a signal of interest. This is particularly important for areas that are deeper inside the brain, because you may actually get much more activation as leakage from areas that are closer to the senses than from areas around your region of interest. There are some ways to deal with that. So at some point, we actually developed an approach to create adaptive cortical parcellations that take the spatial resolution into, or the crosstalk in particular, into account that you can achieve with your particular sensor configuration. Unfortunately, this is not available as a software package, but at least it gives you an idea what can potentially be done. So if you use a parcellation like the Desikin-Kalyani one, I think it's available in FreeSurfer, and you take your regions of interest, and then you compute the leakage from or between pairs of regions, and you display that as a what we call the parcel resolution matrix here. So it's also color coded according to the parcellation here on the left, but every element of this matrix reflects how much one area leaks into another area. Well, then you get a matrix like that. Ideally, you would like to have high values on the diagonal, which means every area leaks into itself, which it should, ideally, and not much on the diagonal, on the off diagonal. So you don't want any leakage between areas, especially when they are distant to each other. And this is not what we get. So in reality, I mean, there are even some areas where you don't even get very strong diagonal elements, which means these areas actually leak potentially more into other areas than into itself. Or they might not really leak into anything really if they're very deep in the brain, for example. So they might simply not be, we might simply not be sensitive to activity from these areas. So what can we do? So we can potentially subsample these parcellations to make sure we only pick voxels that maximally leak into themselves, but don't get much leakage from other brain areas. And if you do that in some principled way, so you've got to get a subsample of the vertices from the original parcellation. So you subsample this parcellation to make sure you get this at least optimal crosstalk among the parcels. And if you then look at the resolution matrix, this parcel resolution matrix, well, it's not perfect, but at the very least, you have this more diagonal matrix now, which means at least every area leaks into itself to a larger degree than before. And these diagonal values, at least, are in general larger than the off-diagonal values. That might not work. That might not work for some areas, especially again the infamous deep regions. So you might not be able to get more leakage from an area into itself than it gets from the more superficial areas. In that case, you may have to remove the area from your analysis. But at least from these cortical areas here that we are looking at here, especially here in this modified parcellation. So for these, it's possible to get at least an optimal parcel resolution matrix. And there are parameters that you can vary depending on how important it is to completely remove off-diagonal contributions. or to what degree you might still want to accept some crosstalk between regions. Anyway, so this is just to highlight what can be done with these concepts and with what has been tried. But unfortunately, it always depends, of course, on what you are trying to do with your own analysis.